Okay. Yeah. Hello, everyone. It's our pleasure today to have James Mingo from Queen's University. James is going to talk about infinitesimal operators, part two.
Thank you.
Please take that part.
So it's been 2 weeks since I talked before, so I thought I'd better just remind everybody about what was going on. So yeah, maybe just a couple of comments about free independence. So it's about distributions of operators. So it's a little confusing because it's highly connected with free products, but actually the free products only come in a peripheral way. It's something about distributions. You don't have things that you're algebraically free. In other words, that they're not free products of some subalgebras. It's a little confusing, and also in some early papers, some kind of algebraic freeness was assumed just to prove something, and sometimes it was lifted. So occasionally you see that popping up, but here there's no assumption about algebraic freeness. So the most basic thing you have is just a unit algebra, a linear functional, and it takes 1 to 1. And some people call that a non-commutative probability space. Some people call it an algebraic probability space. I think I like algebraic because sometimes A is commutative. And so strictly speaking, it should be not necessarily commutative. Okay. And the other thing we had was what I called an infinitesimal probability space. So you assume you already have an algebraic probability space and you add another linear functional. But you don't, it has to take 1 to 0. And the idea is that this is supposed to be some kind of tangent vector. And so it takes constants to 0 because there's some kind of differentiation going on. So it's all kind of loose, but that's sort of the spirit of the thing. Of course, we'll do everything algebraically, so there's no derivatives. But to understand some of the formulas, it makes sense to sort of think of derivatives. So then the key concept, going back 40 years, is free independence. So it's a property of subalgebras. So we often apply it to operators. And if you have two operators and somebody says they're freely independent, just like in ordinary probability theory, although they never state it this way, what you mean is that if you take the universal algebra generated by each of those operators or each of those random variables, then those subalgebras have this property. So it's always best to express it in terms of subalgebras and then specialize it to individual operators. So the statements just come out cleaner that way. Okay, so we say a bunch of subalgebras are freely independent or free with respect to this particular state. Sometimes we have to be very particular about which state we're taking. We say that whenever you take some operators in A, such that each one comes from some subalgebra, but remember they're numbered 1 up to n, so we require that adjacent elements come from different subalgebras, and they all be centered. Centered, like in a random variable, means the mean, the average, the expectation is 0. Then the product is centered. So now this, if you go back to free groups, this is exactly the behavior you get in free groups. So suppose you have a word in some generators. The state is evaluation is to see whether that word reduces to the trivial word. And you say, how can you get a trivial word? Well, each time you must go out and back and come back to a trivial thing, and then you go in another direction of another generator and you come back. but you can't ever go around a square and come back to where you started from because the graph is a tree. So this is just a completely algebraic way of describing that phenomenon. And it's a bit of a miracle that something that simple actually turned out to be useful, because it is pretty simple, but it turns out it is pretty simple. And another thing that's interesting, just from the point of view of the business of mathematics, is that it took about 8 years before Voiculescu proved his big result that large random matrices satisfy this property asymptotically. Because before that, all the applications were to von Neumann algebras. And without that paper, I think the subject would have stayed as just something you use to study free group von Neumann algebras. But it turns out these random matrix examples come in, and now I think they completely dominate the whole literature on the subject, because people in engineering and other areas, statistics, are now just using these tools to compute things, and they completely dominate the number of people doing operator. So the subject has sort of been taken over by applications. Now, what I want to talk about today is called infinitesimal freeness. So it's a property of some subalgebras, but you need to be in an infinitesimal probability space before the question makes sense. And so it's a strengthening of this property. It's harder to be infinitesimally free than it is to be free, because the way I wrote it is the first thing is assume that they're free. And then you add an additional requirement. And this additional requirement tells you something about the interaction between these two linear functions. Because see, here's a formula that has a phi primed and a phi. So it's some connection between them. So up here, they were just completely general things, they had nothing to do with each other. Now we're asking that they satisfy some relation, very special relation. So it says, if I take some centered elements and alternating, so usually you call this property alternating, then that the adjacent elements come from different subalgebras. And centered is this property. So if you take centered and alternating a word, then I can compute its infinitesimal moment. I say, if n is even, I just get 0. And if n is odd, I put phi primed on the middle one, then I don't do anything to anything else. Now, that looks a little strange, but it turns out this is extremely useful, because look, this is a number that comes out. And now I just have a string, but I assumed that they were free. So I have a rule for completely evaluating that. It's a complicated rule, and I can't tell you what it is, but it is a rule exists.
Can I have a problem where if the neighbors on the left and on the right came from the same subalgebra, then when you take it out, you have the, oh, no, it's not a problem. All right, it's not a problem.
Yeah, well, let's do one example like that. So let's do A1, B, A2. Okay, and I'm going to assume that A1 and A2 are from one subalgebra and B's from another, and then those two subalgebras are infinitesimally free. So this rule says this is phi primed of B times phi of A1, A2. Okay, now these guys are in the same subalgebra. So I can't say anything more. The reduction halts. Why? Because I can't tell you what happens inside a subalgebra. Why can't I tell you? Because you never told me in the first place, right? You have to tell me how to do those things yourself. What I'm going to tell you is if you have two subalgebras, how to stick them together. But the individual things I can't say anything about because you never told me anything about it. So it just reduces to that. On the other hand, it says that if I do this, I get 0. That's the rule. And again, this looks so weird that you could say, how could this ever be useful? Well, it turns out, if you go back to these random matrix examples, you have a fixed finite rank matrix, and you look at the subalgebra it generates, and you remember you pad this out with zeros. So you make the matrix bigger by just adding more and more zeros to make it a gigantic big square matrix. And then you have another unitarily invariant matrix. Asymptotically, they will satisfy this rule where this is the normalized trace, and this is the non-normalized trace. Okay, so in the limit, you say, well, yeah, yeah, actually, I mean, it's a little bit, yeah, I have, I mean, what it does to one is a little bit different, because remember that one is not in the algebra generated just on the own by that that fixed finite rank. So I have to say what it is on that one, and I say it kills identity, and it's the regular trace, unnormalized trace on everything else. Okay. Anyway, that puts you into this model. So many calculations that involve these two scales can be analyzed with this algebraic setup. Okay, and then the last thing, yes, get to use the special brush. Oh no, it's wet. Okay.
It was intentionally made that.
Oh, really? Oh, okay. I thought it was supposed to be dry, I guess. Okay. Okay. But then you can't. Have to let it dry. Okay. Okay. Now, the final thing was that if you have an element in your infinitesimal probability space, you say that this is infinitesimal if all of its moments are zero, so if you think in the context of random variables, if you take the expectation of x to the n, that's what in probability theory is called the nth moment. So we're saying that all the moments are zero. Then we say it's infinitesimal. So we don't know what its distribution in the sense of probability theory is just a Dirac mass at zero. Okay. And so the question we want to look at is, we assume that we have two operators in our infinitesimal probability space. We suppose that x1 and x2 are infinitesimally free, which means they satisfy the subalgebras generated by 1 and x1, and the subalgebra generated by 1 and x2 satisfy those conditions. And we also suppose that x2 is infinitesimal. And then we look at two operators, x1, x2 plus x2, x1. And the commutator, I take I times x1, x2 minus x2, x1. So I put the I in because if you're in a C-star algebra and x1 and x2 are self-adjoint, then Q would be self-adjoint. So often, but from the point of view of this theory, this I is just a decoration. It doesn't play any role. Okay, and the problem is, find the distribution of P and Q. So let me just try and elaborate on what I mean by that. So let's just go back to the language of probability theory. Start with a random variable on a probability space. And then we push forward the probability measure. Say that the measure of a Borel subset is the probability that X is an A. And given this probability measure, we can get an analytic function on the complex upper half plane. Given just by integrating this resolvent. A more traditional thing in probability theory would be to integrate the exponential e to the I t x e to the I xt and get the a function on the real line, the Fourier transform. But in free probability theory, the resolvent is more useful. Notice that if z is in the upper half plane, this is a bounded function, and this is a finite measure, so the integral always exists. Okay, and if you take the limit as epsilon goes to 0 from above of -1 over pi times the integral over a closed interval AB of g of x of little x plus I epsilon x. So this is G, capital G is an analytic function. When you as a function of x, it's going to be continuous. So we can integrate this over this little interval with respect to Lebesgue measure. You multiply by -1 over pi. Imaginary part, sorry. Forgot that. So then now this is real. I mean, G maps the upper half plane to the lower half plane. And if you take z in the upper half plane and you take 1 over z minus t, that's in the lower half plane. I want to get a positive thing because I'm trying to get a measure back, so I have to multiply by -1. Where does the pi come from? Well, when you do a change of variable and you bring in the arctangent, you get a pi. Okay. And what does this thing equal? Well, first thing is their measure might have atoms. And so you have to test the endpoints to see whether they're atoms. Okay, so you get mass half. It's just like in Fourier analysis, when you do Fourier transform over and back at a jump point, Fourier splits the jump point into two pieces of equal mass. Well, the same thing happens here. And then you get on the interior, you just get the measure. So what this means, you want to talk about the distribution of a random variable, you could look at the measure, that's one version. You can look at the moments, or you can look at the Cauchy transform, and they're all connected. You can go from one to the other. So knowing the distribution of a random variable means knowing one of these things. Another thing we need to look at a little bit are cumulants. So let me just remind everybody how that goes. So in order to explain what cumulants are, I have to say what non-crossing partitions are. I'm not going to use this very much, so I am just going to draw pictures. So we're always going to look at partitions of a finite set. Say the integers 1 up to 5. And our partition for this thing means to write it as a disjoint union of subsets. And non-crossing means that when you draw this picture like this, the boxes don't cross. So if I put 2 and 5 in the same block, I'd call that a crossing partition, and I exclude that. And if I can draw this such that the lines don't cross, that's called non-crossing, or we could call it planar. In the physics literature, they often call those planar diagrams. Okay, and the construction between the relation between moments and cumulants goes through this picture, and it goes like this. Suppose somebody just gives you a sequence of numbers, complex numbers. Let's call them kappa 1, kappa 2, kappa 3. And I have a partition, and this works even if it's crossing like that. I'm going to say kappa pi is going to be kappa 3 times kappa 1 times kappa 1, because I have 2 blocks of size 1. So each one gives me a kappa 1. I have 1 block of size 3, gives me a kappa 3. So that's going to, I can, if given this sequence, I can say what kappa pi is. Now I do the following thing. I write down some equations. Yeah, so NCN is a set of non-crossing partitions of the integers 1 up to n. Okay, so now you do something a little weird. I'm going to say, I'm going to define, suppose I know the moments. So if given a random variable, we just say m sub n is t of a to the n. So we call those the moments. So given the moments, I say I'm going to define the cumulants by this formula. So this looks like it defines the moment in terms of the cumulants. Because if you know the cumulants, you know kappa pi, and therefore you know this finite set, you can sum and you can compute m sub n. But now it turns out that this process is reversible, because there's only one partition of a set with one element. So this tells you that kappa 1 is equal to m1. You look at the 2 element set, there's 2 partitions, either 1 block with 2 elements in it or 2 blocks each with 1. Okay, and now you see the idea. Suppose I know m1 and m2. Well, then I know kappa 1. So I know this and I know this, therefore I know that. And it just, the same principle just works. When you do this in general, there's going to be 1 kappa n, which you don't know, but you know all the other ones. So you can just solve. It's an upper triangular system of nonlinear equations. Give it a fancy terminology. Okay. Now you can go a little further. This works whether they cross or don't cross, because it's just a triangular system of equations. Now, here's something interesting, which is quite surprising. Suppose I put the set of all partitions in here and not non-crossing, so make it bigger. I'll get some other numbers, some different set of numbers. Those numbers also show up in classical probability theory in the following sense. You take your random variable x, you take e to the I tx. That's another random variable, depends on t. Take its expectation. You get a function that depends on t. You take the logarithm of that function. Okay, you get another function. When t equals 0, e to the I tx is 1. The expectation of 1 is 1, and the logarithm of 1 is 0. So you have a function, that logarithm is a function that vanishes at 0. You expand it as a power series in t, and you write kappa kn over n factorial times t to the n. So you get a bunch of numbers k. You started with some moments, and you got some numbers k. If you put those numbers k in here and you change ncn to all partitions, you get your moments back. So there's this beautiful parallel that you have tensor independence, all partitions. Free independence, non-crossing partitions. And that's been extremely useful that there's these two parallel streams. Typically, you know something in tensor independence, and you use that to inspire something about free independence. Yes, there are some things, but probabilists would probably not admit to as being, I would say it would be a set of measure 0 or a rare event. Just because tensor independence has been around for 200 years and free probabilities have been only around for 40 years. Oh, okay. Okay. So now we can go a little further. So these are just numbers. Now we can do the same thing with linear functionals. You write down this equation. Okay, so now this is an n-linear functional, right? So this mapping could be considered as something from the n-fold tensor product of A and C, because give me n operators, I take their product, I apply this to it, that's going to be a linear mapping from here to here. So I can make each of these guys also multilinear functionals on my algebra. And how do you do that? Well, you just take the same thing and you do the following thing. So the question is, what is kappa pi of an? If I know what kappa n is, I say I take the product over all blocks of pi. I count how many elements are in that block, and I indicate that by putting absolute values around V. And then I just take the elements of that block that are in V, and I just put it like that. So for example, if I did kappa pi of A1, A2, A3, A4, A5, then according to this rule, I'd get kappa 3. But here I just had a number. Now I have a 3 linear function, and it takes arguments 1, 3, and 4. I do A1, A3, 4, and then I have 2 kappa 1s, one of A2 and one of A5. And so this same methodology here will define these multilinear functionals. Okay, so whenever you have a non-commutative probability space, you get all of these multilinear functionals, and these are called the free cumulants. Okay. One little fact that's useful is that this relation over here, just call it star, between moments and cumulants has a relation about, there's a relation with Cauchy transforms. Let me just tell you what that is. If these two sequences of numbers satisfy star, and we let another function r of z to be the sum n equals 1 to infinity of kappa n z to the n minus 1, then r of z is equal to g of z. I'll put a minus sign here, then I'll explain what this means. So this means the compositional inverse. So as a mapping from C to C, I take the inverse function, not the reciprocal. So because in this business, there's a lot of reciprocals, you put these little square, these pointy brackets around here to distinguish between these two things. That's just a reciprocal. Yes, of course, the interesting thing about this function is that its reciprocal is also its compositional inverse. But okay, and that's the relation between them. And actually, from a historical point of view, this is how the free cumulants were first defined. That you took the Cauchy transform, you took the compositional inverse, you subtracted a pole at 0, you got a function. You called that the R transform. And I think when Wojciechowski first did this, given some moments, he could go up to computing the second cumulant. I mean, he got this far, I think, because the algebra is just so terrible. And then Roland Speicher came up with this interpretation, and now, okay, you can do this on your computer and compute 1 billion cumulants if you wanted to. It's completely mechanical now. Okay. Yes, now what about infinitesimal cumulants? Okay, so we just define the infinitesimal moments of an operator by taking the powers and then applying p prime to it. And then we define the infinitesimal cumulants by differentiating both sides of this equation star. Now I have to say what it means. So let's look at this example here. What do I mean by the derivative of pi? We use the Leibniz rule. There's 3 factors. So I'll have 3 terms. Each one will contain 1 primed and 2 unprimed things. And I just put that here, here, or here. So I'll have kappa 3 primed, kappa 1, plus kappa 3, kappa 1 primed, kappa 1, plus kappa 3, kappa 1 primed. Okay, so you just formally differentiate each factor. And that determines the free cumulants. Use the same rule here. I would get 3 things. I'd put a prime in, I get 3 terms, so I can put a primed in each one of these multilinear functions. So that will define free cumulants. Of course, these things are getting really complicated fast. Yeah.
What does the prime do? So I understand the Leibniz part, but what is the prime?
Okay, well, let's do an example. Yeah, well, okay, let's do some examples. So B primed of A is M1 primed. And according to this, it's kappa 1 primed of A. So if I know the infinitesimal moment, I know the infinitesimal cumulant. Okay, now let's look at p primed of A squared. That's m2 primed. By definition, it's the second infinitesimal moment. Then I use this formula. This is, I take the derivative of this guy where I have one block of size 2, and then I add to that the derivative where I have 2 blocks, each of size 1. I just represent them symbolically like that. I don't give them a name. Okay, so this is just kappa 2 primed of A. And now this is a product of two things. So I'm going to have kappa 1 primed of A times kappa 1 of A plus kappa 1 of A times kappa 1 primed of A. Of course, these are the same, so I could just put a 2 in front of it. So this says that if I just say the second moment, the second infinitesimal moment is the second infinitesimal cumulant plus 2 times kappa 1 primed. And now it looks just like differentiating both sides with respect to an implicit variable. Right? You put a primed here, a primed there. Okay, we got a square, so we got to use the product rule. Okay. Now, this looks so formal. How could this possibly yield something interesting? Right? It just, but it's a theorem that it does, that you get some, and the theorem is that, is what I said at the beginning, if you take a unitarily invariant ensemble of matrices and a fixed finite rank one, then asymptotically they satisfy these relations of infinitesimal freeness, and therefore you can use these rules to compute mixed moments. And the mixed moments you want to compute are these guys here. Okay, now there's one other thing I got to tell you about cumulants. And this is their most powerful use. What's bizarre is that it's completely unknown in classical probability theory, although it was known 100 years ago, but you could ask 1,000 probabilists and they would never think about this. In free probability, it's the only thing you ever use. Okay, suppose you're given, I'm just going to give you in the regular case first, and then I'll give you the infinitesimal version. Suppose I'm given some operators. And the question, and you say, are they free? Is there some test you can perform? Okay, there's the actual definition, yeah, up there. But is there some specific test that if you, I mean, of course, it's an infinite number of tests, just like this is an infinite number of tests, because you have to take the subalgebra they generate. Of course, they're all typically infinite dimensional, and you have to check it for everything in there. So it's actually an infinite sequence of tests. But there's a more explicit version of it. And the answer is, are they free? And the question is, if and only if mixed cumulants vanish. Okay, so let me try and explain what that means, i.e., for all I1 up to IN, these are numbers in the set 1 up to S. If I take the nth cumulant of AI1 up to AIN, the vanishing means I get 0 unless all the indices are equal. So in classical probability, remember, we say that two random variables are independent if you have this relation. Right? And in particular, if you take the expectation of the product minus the product of the expectations, you get 0. But this is just these classical cumulants K2 of xy. So K2 is the covariance. K3 skewness. K4 kurtosis. And they don't have names after that. Yeah, because people try to analyze random variables and they say, well, just do the histogram. And they look at the picture. And they say, well, it does something like this. So we got to have a name for it. So they came up with names for those pictures. Okay. So I think I'm ready to get to the main idea in the proof. Or both. I'm going to tell you how you calculate this. Okay. So how to calculate the infinitesimal moments of P. Okay, so I haven't proved this yet, but it turns out that P and Q, this is not too hard to check, are infinitesimal operators. What I mean is that all the ordinary moments are 0. And why is that? Well, when you go to compute, you take a power of P, it's going to be a sum of 2 to the n terms. When you take the nth power, you're going to get 2 to the n terms because there's 2 terms in P to start with. And every time you double the number of terms. So you're going to have xi1, xi2, all the way up to xi2n. And the number of x1s is always going to equal the number of x2s. Right? Because you always do an x2, x1 or an x2, x1. You do 1, 2 or 2, 1. So those are going to be half of them are going to be 1s and half of them will be 2s. Now, we assume that x2 is infinitesimal. So when I write this big moment as a sum of cumulants, infinitesimal cumulants, using this rule here, I'm only allowed to use 1 prime because I'm only taking the first derivative. If I don't put a prime on a box going with x2, I get 0. Okay, so yeah, sorry, I got ahead of myself. I'm just talking about the ordinary moments. Sorry, I'm back over here. I expand this out. So these are going to be x1s and x2s. And there's got to be some x1s there and some x2s. The x2s all have 0 cumulants. So by vanishing of mixed cumulants, whenever I just have a thing that goes with an x2, I get 0. And there always has to be, because half the entries are x2s. So you immediately get that all the ordinary moments are 0. And what we want to find are what are the infinitesimal moments. Okay. So this is just going to be a big sum of terms of the form xi1, xi2, xi2n minus 1, xi2n, where xi1, i2 up to i2n are either 1 or minus 1, or 1 or 2, excuse me, because it's just a product. It's either x1, x2, or x2, x1, so all the things are just their 1s and 2s. And if I take I2L minus 1, I2L, this is either 1, 2 or 2, 1, because just that's the way the word was written. You either multiplied, and an x1, 2 or an x2, 1. So you get that. Okay. And when I try and compute this, so let me just do a case of, I take the fourth power of p. Okay. P, everything in P has 2 letters, so the fourth power of P will give me words of length 8. This is going to be a sum of, I use my formula over here for computing infinitesimal moments in terms of infinitesimal cumulants, or the one where you just differentiate both sides. Okay, and so I do xi1 up to xi8. And I have to sum over all partitions of 8 elements that are non-crossing. So let me just do so half of these numbers have to be 1s and half of them have to be 2s. So let's suppose that I1 is equal to I4 equals I5 equals I8 equals 1, and I2 equals I3 equals I6 equals I7 equals 2. Okay, so half are 1s and half are 2s. Now I have to put in a non-crossing partition according to, and the general formalism of free probability, and each block has to be only a block of 1s or only a block of 2s by vanishing of mixed cumulants. In addition, as I said, in each group of 2, there's exactly a single 1 and a single 2. And by the fact that x2 is infinitesimal means I only have 1 block of 2s. Because when you differentiate, you only put 1 primed. And if I had 2 blocks of 2s, only one of them could have a primed on it, and the unprimed one would give me a 0. So those terms are gone. Therefore, the only term that will survive is when there's a block of size 4 on the 2s. And then you see something. You can either have some x1s interacting, like here, or I could have a single x1 squeezed. So all of the distribution of x1 is discarded except the first 2 moments. Whatever the distribution was, it gets annihilated when you take, and the same happens with the both the commutator and the anti-commutator. It kills off everything except the first 2 moments. And you see this guy is going to give me a kappa 4 primed. So, and this will happen for every term in this power. So what this means is that if I take phi primed of p to the n, it's going to be something times kappa 4 primed of x2. Because whenever I take one of these things, I do this, this would always give me a kappa n primed of x2, that's the 2, times something, stuff. Right?
Earlier you said that you only get their partitions of the x1s, so you don't care about it up to moments, but this is particularly with 8, right? You get longer, more even moments.
No, no. Why? Because let's do 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 12, okay? So we got it out of each guy, out of each of these two, I have to put a 1 on one of them and a 2 on another one. Okay, so now there's going to be 6 1s and 6 2s, and I'm only allowed one block of I'm only allowed one block of 2s.
Oh, yeah.
All the 2s have to be together, right? So let's suppose, yeah, let's suppose I do this. And let's see. Sorry. Yes, okay, so now I've got 1, 2, 3, 4, 5, 6, and I have one guy from each thing. So now this would be an X1, a singleton, and another one. So I'd have 2 singletons and 2 doubles. So in this case, I'd get a first moment and a second. I'd get 2 second moments and 2 first moments. So you get M2 times M2 times M1 times M1. And notice the sub indices add up to 6. So this one would give me M2 of X1, M2 of X1, M1 of X1, M1 of X1 times kappa 6 primed of X2, 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 let's suppose 2, 4, 6. Okay. So because of this thing, you only either get a gap of 1 or 2. And therefore, you only ever pick up the first and second moments. And the same thing will happen when I did the Q, even though there's some minus signs. So in the Q, there's some minus signs that have to be dealt with. Okay, so maybe it's time to state the result. Yes. Okay. So the nth infinitesimal moment is actually can be written like this. Yeah, these are M1 of X. Okay. So M2 of X is just some complex number. So I don't know which number is alpha and beta because I can't tell them apart. It doesn't matter. They're symmetric in the formula. So one of them is one of them and the other one is the other. And yeah, so it's a bit of a miracle because remember I said there's stuff. For example, here's the stuff. But now, okay, there's 2 to the n terms, right? Because there's 2 terms in P, and then you take the nth power, so you get 2 to the n terms. So there's 2 to the n things to add up. But it turns out by a bit of a miracle, you can just boil it down to something like that. Now, yeah, okay, how do you do something like that? Well, you have to parameterize the whole problem. So you have to, it's like in vector calculus. You're asked to compute something, a volume in high dimensional space. So you got to parameterize it, set the integral up, start integrating one variable at a time in the appropriate order, and then you get your answer. What about the other one? Okay, so you get a, I mean, the anti-commutator that's got an extra symmetry, some first order stuff gets canceled away. And again, this is just a complex number, so we don't know which square root to take, but it doesn't matter because we made the answer independent of which one you choose. Okay, and again, it's something they do in combinatorics, right, where you sum these things. Again, it's just like an integration problem. The only difference is in combinatorics, there's no fundamental theorem of calculus. So how do you do integral? You can only integrate over regions where the integrand is constant. Right? There's no fundamental theorem of calculus, there's no antiderivative. So you chop the whole parameter space up into pieces. And then on each piece, integrand is constant. So you just take that constant times the weight of that piece and you sum over all pieces and you get your answer, and then you change the indices and you do these things, and it's this is a case where it's pretty hard to do without a computer. So it's one of those things where you don't need a computer to check the proof, but you'd never find it without a computer. Why? Because who could spot the pattern, right? You've just got to hack away at your computer doing this and that, and eventually you see what the answer is. But I don't know anybody that can just see the answer directly. But in the end, in the paper, you just say, let J1 be the first time this happens, J2 be the next time something happens, and you change the variable, you let K primed be JL divided by 2 something this, and you switch it all around. And there's kind of a combinatorial methodology that's been developed that enables you to do calculations like that. But in the end, we get a simple answer.
Well, it must be a fundamental principle, because if something actually makes sense. I mean, the formula is the answer to something. The formula for something is actually supposed to be meaningful. Then square roots can only appear symmetrically in it.
Yes, well, I think I'm going to turn that over to the logicians. I don't know how to.
Well, I'm not talking about logic.
Yeah, or philosophy or something. There's somebody is up there looking after us, right? That just says it doesn't really matter, but the answer will just be symmetric.
I'm looking for a down word.
Yeah.
Mathematical principle.
Right. Well, yeah, there's, I don't know, but I think I consider it a very interesting question,
Yeah.
but I don't know how to answer it. But it seems to be reliably observed. And in addition, what I noticed you can find calculations related to this in the physics literature. Once somebody gets this and they check it for n equals 1, 2, and 3, that's it. The question is over.
Surely it's just a question of fundamental common sense.
Yeah.
If you write down the square root of -1, that just doesn't make sense.
Okay, you have to make a choice.
If you write the sum.
Yeah.
Of plus or minus, well, of course, that would be 0. Yeah, but anyway, that makes sense.
Well, here's an interesting question for you then, George. Okay, I think we've got 55 seconds left. So in free probability, the most famous thing is the semicircle law. So this thing is z minus z squared minus 4 over 2. But unfortunately, it's got a square root in it. And when you go and do this inversion, you've got to choose the square root in a consistent way for the entire upper half plane. There is no symmetry anymore. And you better get it right. Otherwise, you get the wrong answer. And you have to prove that you can actually do that, right? Because z's in the upper half plane, z squared is in the whole thing, right? It's because squaring doubles the argument.
Sure.
And this just shifts it. So this thing is all the way around, but you got to choose in a consistent way that square, the branch of the square root. You got to find a definition. Okay, I'm just going to leave that for coffee.